This is a two-part video demonstrating how to use Houdini's RBD tools, a set of SOP level nodes that can fracture, set up physical attributes, and even simulate on the SOP level. The first video will do most of the fracturing and set up the bullet solver that collides with an animated ball. The second video tweaks the constraints and using the RBD Deforming Pieces node to create a metal tearing effect. Okay, let's start with the geometry node. I'm going to drop down a cube. I'm going to try and shape this. Let's drop down a transform node. And I'm going to make this box a lot thinner. Squish it down on the x-axis. Even thinner. Now I'm going to make it, scale it up. I want this to be a lot larger now. 5 times larger. Now I want this to be thinner too. Maybe even thinner. Super thin, like it will be a metal sheet or metal plate is what I'm aiming for. We might even get rid of this side, like we might have just a plane instead. So I could replace this with a grid later on just to see which one looks better. This is, I'm gonna move this up so I can have more real estate. So let me rotate this 90, the wrong rotation, the z-axis. So I have this the opposite direction. So I have the normals facing the positive x-axis. This could replace the box, this panel. So this is an option that I can use later on. Either this one or this one. Let me group it. So that should be more clear. For now, let's use the box. Now let's start with the new RBD tools in Houdini 18. It was actually introduced in Houdini 17 or 17.5, but there's been a lot of new features added in Houdini 18 to the RBD tool. So we're going to explore some of those new features. We're going to explore the RBD tools in general. Hit tab, type RBD, and it'll list all the RBD node tools, nodes that are available. The one that we're going to use right off the bat will be the material fracture, because we're going to fracture this sheet of metal into pieces and then we're going to destroy. We're going to hit a ball right at it and the ball will go through the sheet of metal and it will simply destroy it. We're going to have a simple destruction scene that goes like that. So parts of the metal sheet will bend and parts of it will come apart. So material fracture here. I'm going to turn the background darker. So this is a simple concrete fracture and it's doing, however, I want a glass-like fracture because we're going to have a ball that's going to hit it in the middle. And if we're going to hit it in the middle, most of the destruction is going to be targeted, will be focused in the center of this metal sheet. So we want most of the fracturing to happen in the middle. So I'm going to be using the RBD material fracture, which allows us to fracturing by material type. So this helps us fracture our geometry according to by material. And this is super handy. Now we can use glass, which is what I'm going to be using. And as you can see, it has a focus point. It's like a spider web. It focuses the fracturing in at a point and it slowly expands the fracturing outwards towards the edges. As for the wood, it will be splinters of fracture. So as you can see here, we can see these jaggedy lines. So there's like splinters of fracturing. Let's drop down an RBD Exploded View. So let's hit this. Hover your mouse close to the RBD node that you want to connect it to. And as you can see, you can start to see the 3 lines that appear. So that means it's in position to automatically connect it up. So left click and it'll automatically connect these 3 inputs to the, it'll automatically connect the inputs. So let's click under here and this gives us a nice view of how each piece is being fractured. So this is the wood fracture. Now we're going to be using the glass. So I'm going to delete the exploded view for now. Well, actually, let's move it to the side. I'm going to give it a black color because we're not going to be rendering this. This is only for debugging purposes. Let's go back to the RBD material fracture. I'm gonna do a bit of explaining on this. There's 4 inputs. Now there's the geometry input, the constraints, and proxy, and Voronoi points, the extra Voronoi points. So as I explained in the previous video, this Voronoi points is similar to what we did before with the Voronoi fracture, the second input, where it accepts custom points that will drive the Voronoi fracture. This is very similar to this. It's the scattering where you scatter all the points all over the geometry. This is exactly the same thing. Now, the RBD material fracture node also has 3 outputs. Now, it's outputting the geometry, the constraint, and the proxy geometry. Now, the constraint should be pretty... If you've seen my previous videos explaining simple destruction, there are ways to glue one. You fracture, you have your geometry, you fracture it into pieces. And there are things like glue constraints, which will keep the pieces held together tight enough to withstand certain collisions. So it doesn't fracture altogether. It will slowly fracture certain places. So if you're rolling, it's like having a huge Lego ball, like a ball made out of Lego, and you're going to roll it down the stairs. So it's going to fracture piece by piece. It's not going to come apart instant. But how do you want to control how it breaks apart? That will be controlled by glue constraints. So that's what this middle output would be like. We can actually put a null here. If we put a null to the geometry, so this is going to be geometry, it's no difference. It's just this. This is the high quality geometry. Then let's put another null onto the constraints. Now this instantly it looks different. The constraints, which are glue constraints, there's different types of constraints, but let's focus only on glue constraints. The glue constraint, which is how well do you want this geometry to be held together? How well do you want it to bond? How strong do you want it to bond? Piece by piece. This piece, now this is very confusing. Let's go to a simple one. Let's go to the concrete. Okay. So we have a few pieces. This piece and this piece, how well it's held together. That will be defined by this line. That's what this line will tell us. It's going to be held together at a certain strength. It depends how much force we apply at this geometry. It will break. If the force is great enough to break this constraint, then these 2 pieces will start to fall apart. Will start to fall further and further, get further and further away from each other. Thus, it breaks. So that's what this gives us. So let's, inside the geometry spreadsheet, these are primitive. So it's going to be in the primitive section. This is all generated for us out of the box by this RBD material fracture node. So that's very convenient. I mean, before we would have to set this up manually or use the Voronoi fracture node to have it set up for us. Now there's a third input, the proxy geometry. It's a low poly geometry. Why would we need a low quality version and a high quality version? This will become more apparent when we use RBD interior noise. The interior noise will add more polygon to geometry. In most cases, the high quality geometry isn't necessary for the simulation. It's not really important, the simulation. And there's more points on the high quality geometry that's not necessary for the simulation to know about. Like, the simulation doesn't need to know about that little bump or that little noise chain. It doesn't really need to know about that. It just needs to know approximately how big you are in order to calculate the collision. So this will be used for the simulation, for the solver to calculate. This is mostly performance improvement. Now, I've separated the outputs into 3 null nodes. You don't actually have to do that to access it. If you come here, go to the I, or you can just use the geometry spreadsheet down here. I'm gonna lock this. There's now a drop down. So this is very similar to the vellum nodes, where you can access all the information here just by dropping this down. So you can do the same thing here. This gives you even more detailed attribute. This is all the proxy, and this would be the primitives, vertices, points of the proxy geometry. Or if I want the high quality geometry, it could be here, or the constraint geometry, whatever you wish. However, if you want to view a particular output in the 3D viewport, the only way that I know is that you have to put the 3 nulls here. So it won't show on the 3D viewport if you go like this. Like this doesn't change the 3D viewport. If we go here and I change this to constraint geometry, the 3D viewport is still showing only the high quality geometry. It's not showing the constraint geometry. This does not affect the viewport. So the only way to view it in the viewport is to go here and put the render flag on this. Okay. The idea of the scene is to have an animated ball to hit the center of this metal plate or this metal sheet. So I think this is a good time to animate the ball. So let's call this metal deform because it's going to be deforming. Let's add another geometry node, and this is going to be where we're going to animate the ball. So drop down a sphere. I'm going to drop down transform node. I think the sphere should be a little smaller. Oh, this is going to be the animation. Let's drive it back on the x-axis. So start off here. Say this is going to be our camera. Okay, we should pick a camera angle first before we start animating. This is a good, because we want to see the ball coming through and we want to see some of the debris that flies off on the other side of the metal sheet. Let's put down the camera. I'm gonna be 640, 640, so it'd be faster to render. Let's see, animation. Let's drive this closer. Let's go, okay. This right at the edge of the camera. So put down a keyframe for this parameter. Hold down Alt and left click the translate. This will create a keyframe on frame 1. Now it's going to travel, let's say, so we have this set at 24 frames per second. So here would be 1 second. This would be 2 seconds, and this would be 3 seconds. So I want this to hit, say, 2.5 seconds of animation. We could adjust this a little later. So let's go with that for now. Have 2.5 and add another keyframe by Alt and left click translate. So this is the second keyframe. Wind back, play it. That's, oh, and check this. So this will play in real time. That's pretty cool. We can actually do a little more to the animation to have it more smooth. Select this node that contains the keyframes. Come here to Windows, Animation Editor. Make this a little bigger. Now have this mouse here, press F, and it will focus the screen on the keyframes that you have created. So there's 2 Bezier curves. I want this to appear to whoosh and slow down. Actually, whoosh, I want it to slowly come in, speed up, something like that. Bring this low, stretch this over here a little bit. So this is slower, fast. This is where it hits. Maybe make it a little lower. So it hits a little slower. You can have a more clear effect. Doesn't seem like there's much difference, is it? Okay, I think that's okay. This is going to be a very simple animation, so I don't want to spend too much time tweaking that. So we have our ball animation. Go back to the middle deform. Now that we know that the ball's going to hit in this spot right here, so we can actually see where it's going to hit. That's why I wanted to animate the ball. I'm going to turn this into a glass fracture because I want that spider web. I want that spider web fracture to be here, but I like this focus. Like I like how the glass fracture focuses all the fracturing pieces in the center here. Now we can control where this goes at by feeding in some Voronoi points here. So let's add a point. Template this. Add. Check this. So we're adding a point. I'm gonna make that point a little larger. So that's this guy right here. Hook this up to this 4th input on the RBD material fracture. Okay, nothing happens. Oop, nothing happens. It's not affecting this fracture. Is not affecting this point. Is not affecting the RBD material fracture. Now the reason behind that is because we have to enable it. Now this scatter points, we don't want to use this. So the impact points, we don't want to use this. This is the out of the box one. Once we uncheck that, there will be no fracturing. Because there's no points feeding into it. Now what we want to use is our input points. Now I'm going to hide the ball for a second. So this is fracturing where the point that we added. So now what we can do is take this point, select the add, come over here, press enter, and then press, if this widget, the transformation widget doesn't come up right away, you can press T and then it'll come up. And if you want to change the camera angle while you have this widget, hold Alt and you'll see that your mouse turns into a hand icon, and you can actually drag, pan and when you let go of the Alt, it will go back to the transformation widget. So this is very handy to flip between perspective camera changing mode to the transformation widget. And I'm going to move this around. Now as we move the point around, we can see that the RBD material fracture will update interactively. It'll update right away. So this is incredibly handy if you're trying to get a very specific fracturing effect. This is super handy. Now I'm gonna bring the ball back in. So ghost all, because I want to know where it's gonna hit. So it's gonna hit around this. So let's take this and put it in the center, which is actually at 0, 0 point. So we could have just left it at 0, 0, 0. But anyways, I wanted to demonstrate this interactiveness with this widget. So after you're done, put the render flag back here. I'm going to turn off that. If you want to get out of this mode, just press escape. So now we have the fracturing happening here. So the point is that this ball will hit this origin, the focus of the fracture, and some of these pieces will bend. Some of them won't, but we don't really have enough fracturing pieces at the moment. There's not enough for this to go through. It's just gonna it's not gonna look properly. We need a bit more fracturing pieces. Let's go here. Let's turn off the ball for a second. Come to the RBD material fracture. Let's look at the cracks. We can increase the number of cracks. So if I turn this up to double, it will crack it everywhere. There's a lot more cracks. However, that's not really what I want, but this will increase the number of cracks, the number of lines. So that's what that does. This is a variance. So this is what's the noise that you want. You don't want, if we put 0 for this, it's just going to be, you'll see that every single slice is very equal. So that's not what we want. You want a bit of variance to have it look more interesting. So that's what this does. And this is the seed. This is like if you want a different type, you just want to like browse through, just give me something different. So that's what this does. Concentric crack. Now minimum width. This will determine how the width of the space between each circle. So this small circle and this small circle. So if I want this width to be bigger, just increase this number to be bigger. However, so okay, let me do this. 0.2. Now this might not be what you expected. Where's my circle? That's because we have to actually enlarge the circle. The concentric crack area. It has to be expanded if you want to get more concentric cracks, more circles. So let's lower this back. Discontinuity size. I'm gonna try 20. Yeah, so this expands it. This will expand the concentric cracks area, and then you can increase the minimum width, and then you'll have more larger pieces, larger slices here. Now I want to expand this even further. So let's go 10, even more, 5. Even more. I'm going to leave it at 1. Okay, that's getting a lot better. Now I want these pieces to be larger. So I'm going to make this even larger. Even larger. Okay, that's pretty good. You can even control the spread. So say I'm going to spread this out. It's no longer symmetric pieces. It's less symmetric. The circles are less. It's less circle join if you increase this number. The impact is spread out. It's not concentrated in that circular pattern is what how I like to think of it. And this is the discontinuity frequency. How often do you want it to appear? I'm just going to leave it like that. You can you can like play around with these settings until it gets the look that you want. Okay, so the RBD material fracture also comes with chipping. Now we're not going to be using chipping for this. This is when you have smaller pieces that gets blasted out. That's what this is useful for. However, for this particular scene, I don't really need it. It's also pretty CPU intensive, so I don't really like enabling this unless you're doing something, unless it's the final run. It's like the final version. During development, I would like to keep this off. Details. Now, this is turned on by default. Now watch what happens when I disable the edge noise. We get straight lines. So that's what this does. Edge noise. That's pretty intuitive. It just blurs this noise, these slices, these lines. I'm not going to go over in detail what these parameter does. You can just play around with it to sort of get like the desired effect. Now, constraints. The constraints is the glue constraint. So this is quite new. Like, we get this right out of the box. We no longer have to set up, like the Warner fracture actually did this for us as well. It comes out of the second input out here. But after this wasn't out of the box. Like, it is out of the box, but after we had this only added the rest length for us automatically, and we had to name it manually. So after this, we had to like do an attribute create and name the constraint name. So if you watch my previous video, I go over this in more detail for the Warner fracture. We had to name it manually and give it a primitive, a string, and then give it a name, glue. So we had to do this for the Warner fracture. Now for the RBD material fracture, it does it automatically for us. So if I bring this up, geometry constraints, piece primitives, constraint name. So it comes automatically for us with the rest lengths and even the strength. It even comes with strength for us. So this is super handy. So I don't want 10,000 as the glue. That's way too strong. I'm gonna lower it down to 1,000. Let's get rid of this. Okay, and we are ready to do a very simple simulation. So let's go to RBD and let's see what we have. We now have access to the RBD bullet solver. So the bullet solver can be placed right on the SOP level. We no longer need the .NET node. So let's place it right down here. I'm going to hover this over so I don't have to. Okay, there we go. Oops. However, this I'm going to shake loose. I'm going to place it here. I'm going to manually do this one. Now, the RBD bullet solver. It comes with 5 inputs. The geometry, the constraint geometry, proxy. So we all know what those three inputs are for. It has a collision geometry. So this will be where we hook up our animated ball. This one is the guide simulation. The guide simulation I'm not going to go over in this video. It will be covered in a different video. So basically what this one does is, how do you want to control the fracturing? If you see my previous video on external forces and how to set up external force fields affecting the RBD simulation, this is very similar, except this is way more cooler. You can actually place animated geometry, and it will use that animated geometry as a guide to affect the RBD simulation. That is way more handier. As if you've seen that previous video I did, it was a quite elaborate setup just to get that working. Like this, with the RBD tools, you get it right out of the box. That is so much more quick and easy. The workflow is so much more easier. But this is not covered in this video. The guidance sim will be covered in my next video, which is in the works. Please stay tuned for that. So let's hook up our animated ball first. So let's bring that in. Go here, ball animation, out render, oops, into this object, and let's hook it up to the collision geometry. Now let's look at what outputs the RBD bullet solver has. It has a geometry, it has a constraint geometry, proxy geometry. So we all know what those are now. I've gone over it a few times in this video. We also have simulation points. We're not going to be using simulation points in this scene. I'm just going to play it. Let's go back to our camera angle. Okay, let's play this. You can obviously see a few things that are wrong. One, our metal panel just falls straight down. So that's not what it's supposed to do. That's not what we expected. And the second thing, the ball is not moving. Let's fix the ball animation first. So select the RBD bullet solver, come over to the solver tab, and we have a bullet object. We have collisions, and down here, initial object type. It says create animated static objects. It's actually create deforming static objects because the ball is changing every single frame. So you want the solver to update every single frame. If you have something like that, then you need to create a deforming static object. So let's check that. Choose that. Rewind. Okay, so we solved one problem. The ball is moving. Now, second thing, this our geometry is falling to the ground. That means if we look here in the RBD bullet solver, ground, well, we don't have a ground. We actually don't need a ground for this particular scene. But if you wanted to add a ground, this is where you would do it. You can just press ground and it'll add a ground plane. But I don't need that. Forces, it has gravity automatically added for you. So that's handy. Gravity is good. However, I want this metal panel to stay hanging. I want it to stay in place until the ball hits it, and then the pieces can start flying off. So let's move this down. Let's move everything down so I have more real estate. Now I'm gonna bring RBD configure. Now what this does, this can set the physical properties of our geometry. So let's drop it down first, and I'm going to drop it in between these two. Okay. So this comes with 4 inputs: geometry, constraint, proxy, and static bounds geometry. It outputs geometry, constraint, and proxy. So these 3, we know what they are. What's interesting is this one. This one is a static bounds geometry. We can disable certain pieces of our geometry, of our fractured geometry. So what I want to do is disable the pieces on the edges. These pieces, I want them to stay put. I want them to stay hanging in the air. So I want to disable them. If we disable the pieces on the edges, it will hold up the entire fractured panel long enough for the ball to hit through it, to collide with it. That's because we already have glue constraints set up. So it holds it enough. The glue constraint plus disabling the pieces on the edges will be enough to hold it in the air. This node, not only we can control which pieces are active and which pieces are deactivated. Now this isn't really new. I mean, this node, this UI and this workflow is new, but setting pieces to be active and disabling them in the simulation, this isn't new. This is like, it's always been there. It's always been in bullet solver world, but you had to do it manually. You had to deactivate it manually. So you can still do that. So that was always there. However, it's been made in the RBD tools. It's a lot easier to set it now. Everything's done out of the box for you. I'm just going to show it to you first. Okay, I'm going to drop down a cube. Template this. The box. Drop down a transform. Transform the box so it's a little larger. So I want this to cover everything in the middle. Okay, let's make it a little smaller. So okay. I think it would be easier if we have a sphere. Gonna change this to a polygon. Frequency. Okay. So we have a little bit of smooth sphere. Now I'm gonna make this smaller. Okay, so I want everything that in this area of this fractured piece to be active, and everything that is not covered by everything else on the edge points to be disabled. So let's hook the static bounds geometry. So this will be our bound. We're defining the bounds. So let's hook that up. Check this. And come to the RBD configure. Now, down here in the bullet data, we can enable this activeness. And then how do we want to do that? We want to use the bounds. So check this. Now, how do we know it's doing what we want? Now, in this visualization, we can choose active. Now, it will show us all the green pieces are active and the black pieces are disabled. So we can template what we had. This is our sphere. This is what our bounds area that we were defining. And we're telling the RBD configure that's what we want to do. Now come over here, disable this first, and then come to the bullet solver here. Now let's try this. Let's give this a try. See if it's actually working. Okay. Well, first of all, there are things that we're not quite done. So there are a lot of issues, but we have successfully have our metal sheet hanging in the air. So it's no longer falling to the ground. It is punching a hole through it. Some of the pieces are coming loose. Some of them are still intact. Well, there's one more thing I want to configure first before we start solving all those issues. RBD configure. We can actually define the physical properties of our metal sheet, of our fractured pieces. So this is going to be a metal sheet. RBD configure, come down here, physical attributes. This, you can choose one of these 4 types. I'm guessing sidefx will grow this list as they develop it in future versions. So expect that you're going to have more types in the future. We want this to be a metal. Now we can choose what type of metal. I'm going to just use tin. And this dry and clean, we'll just leave it at that. This is probably for friction. So let's try it again. Okay, so it's a lot better. But this is not even close to metal. Like, it's just breaking like as if it was just glass or something strong, like hard. I want metal should be tearing apart. Especially if it's tin. It should be like tearing through this. So pieces should be bending and all that. There's more that we can configure in the RBD bullet solver. I'm just going to go over these tabs. I think it's time to go over some of these the RBD bullet solver tabs. Let's just go over this a bit. Now we have the solver. We know that the bullet object, we have all this, the physical properties. So this is what initializes with. Collisions. Now this is the ball. This is the animation ball. This will define that. So you have to check this. If you uncheck collisions, you can see that our ball goes away. It will not use the animation. It will not use any collisions. So even though we have it hooked up, you still have to check this, enable this. This is the ground, and then we have our forces. Let's go to constraints. Now the constraint tab. This will define what constraint, the name of the constraint, which is glue, which was set up in the RBD material fracture constraint tab over here. So this defines the glue connections in the RBD bullet solver. We have to hook those glue constraints that we defined over here to the actual glue type constraint. Because there's several types. There's a glue, there's soft, and there's hard. There's actually even more. There's like hinges, there's pins. So you have to like link it. Like this, the glue is the name. Sorry. Glue is the name of the constraint. But say if I come here and I change it to something constraint. Now that's not going to get recognized in this bullet solver. The glue, this is not going to work. If you play this, it's just not going to work. It's not, the glue is not holding up. It's just getting random stuff. You have to go here and you go something constraint. That's where you choose it. And if you play it again, So this is what we get. We get our original. So let me change this back to glue. So that's what this tab does. There's a second part to this video, which is a direct continuation from where we left off. In the second video, we'll start to tweak the parameters in the soft constraint in order to get that metal tearing effect. And I'll be using the RBD Deform Pieces node to get that metal deformed effect. Please check that out. Links in the description.